Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward.
Hello.
Hello.
It's just us this week.
Just us.
Yep. Yes. This week we're going to talk about the future of programming, which is something that has been building up for a long time. I did a presentation at PyCon on rethinking objects, and there was a whole lot of research into other programming languages and sucked me into Rust and all that kind of stuff.
Yeah.
Before we get started, though, want to remind everybody that we've got 2 developer retreats coming up. The one on July 17th, which is in
a couple weeks.
10 days. 10 days, basically. It's 10 days. That's basically we do them for approximately 5 days. This is very low ceremony things. The theme for that is concurrency, although if you want to come up and work on whatever you want to work on, there's basically no structure. We make it up as we go, and if the weather's nice and we decide we want to go, take the ski lift up to the top of the mountain or go do outdoor activities, we do that. I did check with the marshal, and it is totally fine to put an RV in somebody's driveway or camp in people's yards. I've got a little side yard here that people can set up a tent in, and so
if you want to come to Crested Butte, hang out with some nerds, talk about concurrency or other things.
Mm-hmm. Yeah, and if you go to the WinterTechForum.com website, there's a thing about travel. So getting here cheaply is if you take a discount airline into Denver, there's a way to take a bus that takes you right to the middle of Crested Butte. I've ridden it. It's actually quite nice and
pretty easy.
The easy, cheapest, most reliable way to get here. You can also try flying into Gunnison, but that's a very hit and miss kind of thing in the summer.
Yeah, and once the afternoon thunderstorms start happening, it gets tricky.
Never know. So, and then on August 14th, we're going to do another one, which is on the Rust programming language. And so we'll just be exploring that. So just if you are interested, go to the WinterTechForum.com website, and there's
registration form there.
Well, no, you're not registering. This doesn't cost anything. This is just, but to find out about it, you get onto the Slack channel.
That's right. And Slack is where the communication happens.
Slack, where all the communication happens, and so if you have questions or anything, you can ask them there. And so yeah, it's an adventure.
Yeah,
and we always learn a lot of. At these things, we learn a ton just because we're exploring.
Yeah.
So that's coming.
Great. Exciting. Okay, let's talk about the future of programming. So you and I last night were brainstorming, and we came up with a long list of what the future of programming looks like.
Yeah, way too long.
So, but we should just start going through it.
Yeah.
So let's start with your presentation from PyCon and what you talked about there.
Well, so that was started because there are people who in recent years, they started going, objects were a mistake. It was all wrong, and we should never have done objects, and it should all be functional programming. So I'd listened to these, I noticed these things and kind of shrugged it off, and I thought, well, maybe there's something to what they say. Obviously, there is a lot of value in functional programming, and so maybe I should look into that. And basically, I found that the people who were saying, oh, it's a total mistake, they never really made that strong of a case. But at the same time, you look at some of the more modern ways of looking at objects. In particular, I found myself interested in the way that Rust did it and the way that Go does it, which is a data structure and then associated functions. And that I have gotten very attracted to, and Python has added the data classes so that creating reliable classes is much easier. So there's a lot. I can see the movement towards it. But what I did was I went back and I looked at some of these earlier languages, kind of like, well, how did we get here? And so you look at languages like Pascal, and one of the things that I remembered was that, oh, Pascal's very weird. It has functions and procedures, and they're the same, except that functions return a value and procedures don't. What is up with that? And what I realized is that most of the people at the time were coming from, like, I don't know, everybody at least had some background in assembly language. And so the whole reason for that dichotomy was that an assembly language programmer would look at this and go, oh, that's so wasteful to return a value that you never use. Oh,
okay.
And
efficiency oriented.
The idea was context.
Yeah.
It's like, okay, in this context, these things made sense. They don't make sense to us anymore.
Mm-hmm.
No language would do that because the compiler would take care of it, or, it doesn't matter.
Yeah.
And so, but at the time, these things made sense. And so I began seeing all of this as a process of evolution. And it was, well, in the current context, what are people able to understand and absorb, and we're talking the middle of the bell curve. What are people able to take in? So if you look at it in terms of evolution, you go, oh, the whole industry is now in this place rather than that place.
Mm-hmm.
And so we're able to do, we're able to grok languages like, Rust, and we're also seeing, well, this is, Richard Feldman did a talk sometime in the last year where he talked about dynamic languages, and his question was, will we have any new dynamic languages? And his argument was that, well, look at where all the dynamic languages appeared. It was when the internet came in, and we were just like throwing websites together.
Move fast and break things.
And if things broke, well, what would happen? What's the worst that could happen?
Yeah.
Oh, the web page looks wonky, or it doesn't come up, or whatever. It's not the worst thing in the world. So a dynamic language was a faster way to do that. But and he showed in a chart, he goes, okay, all the dynamic languages happen now, and all the arguments that you would make against dynamic or for dynamic languages. Oh, it takes too long to compile if it's a static, and all of these things. He went through and he kind of said, okay, we have better programming technology, we have faster machines, all of those things go away.
Yeah.
And so his argument was,
the value of dynamic languages is just diminished over time.
Right.
And the future is very clearly statically typed languages.
And he also noticed the trend of languages like, well, JavaScript, now we have TypeScript, which adds types. With Python, there's type annotations. And so we're all moving towards this, some flavor of static typing because you get so much value from it.
Yeah.
And so, which I just thought, boy, he's right. I can't see another dynamic language arising at this point. We are moving towards
not a mainstream one for sure.
Yeah, sure. As in, like people have always created lots of different languages, but the ones that actually take hold need to give you a lot of bang for your buck.
Yeah. I'm very clear on my view that statically typed languages are the future. Like, there's just no good reason why that's not the case.
And many years ago, I wrote a blog post called Strong Typing versus Strong Testing, or something like that, where I made a case for why dynamic languages are great. And I look back on it now and I realize, because all of the static typing mechanisms that I had used were, incomplete. And so you would jump through all these hoops and you wouldn't necessarily you'd get benefits, but not like now. Well, for example, Java. Okay, yeah, it's statically typed except for null pointers. Null exceptions. they drift through the whole system, and it's like, okay, that doesn't seem so great, because you're doing the work and you're not getting the benefit, and you have all the issues around Java.
Yeah.
And so now I look at it and go, oh, the reason that made sense to me at the time is because I had never seen a really complete type system.
Yeah.
And you look at something like Rust, and it's just, I don't know, it's very elegant.
Yeah.
It's they've learned.
Yeah. I think there's all sorts of ancillary benefits that now are so intertwined into statically typed languages that the benefits are
overwhelming. They are.
So now the IDE support, when you actually do a dot and see what options are available, it's accurate with statically typed languages. When as soon as you make a code change, you see red squigglies if you've violated some type thing. Type inference in the compilers has gotten so good that you can most often in modern statically typed languages specify types when you want to and leave them out when you don't want to specify them.
Or when it just gets too hard to figure out what that type would be because there's generics and all kinds of other complicated things, and it's like, oh, it'll figure it out. Oh, that's nice.
So I think I very clearly this is the now and the future of programming. I don't see us going back to dynamically typed languages ever.
No. No.
Maybe there'll be some crazy innovation in type system, type theory that gives us something new, but we're not going back to dynamic.
Yeah, I have to say that the improvements that have been made in the typing systems for Python have just been so pleasant. They basically looked at what Scala has done and what other things, but I mean, you're able to use union types to describe things, and it's just so clear.
Yeah,
and then you can run the type checker on it. It'll point things out if you're not doing it right. And
years ago you made a point on this whole topic that I thought was really insightful. You said that the type should exist to serve the developer, not the compiler. Like you as a developer, you don't want to be a slave to like getting these types to fit. You want the types to give you a lot of value. And I think that that's what we've seen that has really shifted this, is that now the types exist for you, the developer, not so much for the compiler.
Yeah, I think
like characterize that right?
Variance is a good example. It's like the hoops and the mental twists that you had to put your mind through to understand, am I doing the variance right? And the compiler would insist that, oh no, this isn't, you didn't do that right. Well, I'm thinking of Java, of course. And one of the things that I am just kind of fascinated by is how Rust managed to eliminate the need for covariance and contravariance.
Yeah.
They just
no inheritance.
Yeah. And some of that is actually because of the lifetime system. And I think the other thing is that it follows what C++ did with templates, with Rust generics, is that it actually makes a copy of that for a particular type. But then everything, you get the full type checking, but then you don't have to think about variance. And it's like, well, that one just kind of blew me away. It's like, oh, well, I'm a bigger fan now.
Yeah.
Because not having to, and that, to me, that is okay. They did the work so that we don't have to think about that problem.
Yeah. And I think from what I've seen with Rust, it doesn't give you inheritance, but at least you have type classes, or I don't know traits, I guess they just call them. And you have another way to accomplish some similar things.
Sure, you can create an object and you can call a method on the object. So you're able to do that, but then it's got this other, I mean, the way the traits work is more like what Scala's type classes are like. And so you can come in and you can go, oh, I want a new feature for this class or this trait, and so I can add something to it, and it just works seamlessly. And compared to all the things that we've piled on object-oriented languages in the past, I like this so much better. It's just so much cleaner.
Yeah.
And of course they were able to learn from all of the experiments that had been done in the past and do it right.
Yeah.
But it really changes my perspective on this. I go, yeah. And the idea that you create the data structure, you automatically get a constructor. You don't have to write the constructor. There's a default thing for it. That is very appealing. You're not dealing with, because you don't have inheritance, you use composition, and when you know what's going on underneath the covers with inheritance, you're going, oh, it's really just composition and some magic. But the magic causes a lot of problems. You get if you try and do multiple inheritance, you get the diamond problem. It's like, well, no, you stick two objects in your new new object, and you're done. You don't have any diamonds or anything like that. There's nothing. It's like, oh yeah, that's the part where I go, okay, I'm not going to say objects were a mistake. I'm just going to say inheritance was probably a mistake.
Yeah.
Because it's like, it made us go down this weird alley of, well, okay, we got to reuse code through inheritance. And it just added a bunch of really messy stuff. And then you'd have deep inheritance hierarchies, and you'd have all this stuff. And it's like, yeah, that part I think did not work out well.
Yeah.
And so
we've learned some better ways.
We have learned some, much better ways, much cleaner ways. Because things just, we had to add messes on top of messes to make things happen. So.
Okay, so static types, a move towards, I don't know, a different way to do data modeling through maybe like ADTs, some types, product types, traits, and enums.
Well, see, there's an example. Enums, I feel like I remember Martin Odersky at one point going, enums, that's, we can put something in, but it's not that big of a deal. But then with Scala 3, I think he got it. He was going, oh man, enums are just, and again with Rust, the enums are really clean, and they cover all the cases pretty effortlessly. And then you add pattern matching on that, and you
exhaustive pattern
matching and everything, and it's just so much cleaner. You get what you need to do, but it doesn't have all this extra baggage that we accumulated in some of the older languages.
Well, it's interesting if you go back to Gang of Four patterns and some of other patterns, they were really kind of, I think, working around the limitations of OO to be able to accomplish some particular thing. And it's like, no, I don't need to use the visitor pattern anymore because I just have my enums and pattern matching and I'm good, and traits. Yeah.
If you want it, because the visitor pattern, and a lot of people were really confused about what the visitor pattern was for. It's for adding new methods to an existing class hierarchy. And that was not clear because of that, there was all this dynamic calling back and forth and everything. And so you go, oh, that must be what it's for. But the goal was to say, you got an existing hierarchy that you want to set it up so that somebody can add new methods to it later without touching that hierarchy. That was the whole thing.
Yeah. Oh, and now we have type classes and traits and Rust and pattern matching, and hey, we can.
You can just do it. It's just
so
you don't even
more
think,
clear.
Oh, what's the problem? It doesn't even occur to you. You just go, oh, I want to add another method here.
Yeah. So we mentioned IDEs, and I think that is very clearly a key element of the future of programming. It's like if you are not, as a language designer, creator, maintainer, whatever, if you're not thinking about how to provide amazing IDE support, then this is not going to succeed. Don't bother at this point. I used to write a lot of my code in VI with no assistance from an IDE, and no plugins, just write the code, and constantly looking at the APIs and writing the code without any help.
Right.
Those days are gone. Like anyone that is not using a tool to help you write code is just wasting their time. And so this is, I think, at the core of some of the complaints about the future of Scala, is that the IDE support has not evolved as well as with some of the other languages who are more focused on the IDE support. And I think John DeGoes points this out in his blog post about what he would like to see in the future of Scala, and then his follow-up blog that is
I'm giving up on Scala.
And I think part of that was that the IDE support was just never sufficiently invested in.
Oh, we've experienced that. It was just like, oh, IntelliJ hasn't caught up yet, or it was just, is this wrong? Yeah, that lack of instantaneous feedback, which we used to just live with. Oh, when you run the compiler, you'll find this out and you'll go back and fix this. Now it's like, if you don't get correct red squigglies or little indicators that that something's wrong, wow, that just slows you way down. Boy, our expectations have been raised.
Yes, they have, and for good reason. Let's have good tools that help us write good code. Obviously, I'm writing a lot of Kotlin now, and the IDE support is
stellar,
really amazing. And
because the company that makes the IDE made the language.
It's clearly a focus and an important thing for them. And so I think the bar has been raised, as you said, and very clearly the future of programming is using sophisticated tools. I would even include AI as one of those tools.
Absolutely include. I mean, my experience with just the little experiments that I've done with AI have been, what I've found is that I go, oh, I'm doing this thing over and over again. I guess I could write a little script or something to do this, but it's going to be a pain. Wait, I could have the AI do it. And it does. And it's, I mean, the leverage that you get is tremendous.
The mundane stuff, we outsource the mundane stuff to a large language model, and
as long as you understand the code that it's writing, it's like, I'm totally fine with that. I mean, it gives me that leverage.
It's just another tool.
It is.
Help us be more productive.
It's another tool, and
I think we're just at the beginning of that. There's so many places where this is going to impact how what we do as programmers.
It's going to, this always happens when we get more powerful tools. People are going, oh, the skills that I had before writing assembly language are now going to be useless. And it's like, yes, but now you're able to make more complex systems. And I go into, stores, or, like the bookstore here, they're using antiquated software because there's not enough bookstores out there to justify a team of people writing new bookstore software. But one person and a good AI could develop that. And it's like, we have way more needs that are unfulfilled that it's going to help us do. And we're going to get to this point, we're just going to go, yes, now it makes one or two people, it gives them enough leverage that they can create a product that plenty of people need, and they're actually able to make it, whereas financial justification just wasn't there unless they had that tool. So
IDEs, tools, better tools.
Yep.
On the tooling front, I think we've also seen that a lot of the modern languages have kind of an end-to-end tool chain built into the language, essentially, or built into the artifacts that you get when you want to use the language. And so this is all the stuff from compile, test, dependency, pulling dependencies, resolving dependencies, lint, formatting, profiling, like all the tools.
Project
initialization.
We'll just do all the stuff right for you, rather than you going in and going, well, okay, so I write this code. Now, what are all the other things? Oh, well, maybe I can ignore them, and then you end up with an incomplete thing. And And I think a lot, well, like one of the tools that I'm working with now is Rye, which is a new thing for Python that is modeled after Rust's Cargo, which is like, okay, do everything for you, including install your Python for you. So
I've been searching for that in the Python world for at least a decade.
Right.
And I can't wait to try Rye, because maybe it will finally be the thing that I'm like, yes, they finally cracked that nut.
That is the goal. And this is, I forget the name of the guy who's doing it, but he's a brilliant designer. And his model was Rust's Cargo. And it's like, oh, look how Cargo does all this stuff for you. It sets everything up correctly. It handles, versioning and, anyway, all the stuff it handles for you. And so you don't have to learn all of that out of it. And so
batteries included.
Total batteries included. Yeah.
Yeah, I'm excited to try that. Gradle has something called Gradle Toolchains. Maven, I found a plugin that does something kind of similar, but this is bootstrapping the JVM that's needed to build the project for you, which is really nice. The downside with Gradle around this is that you still need a JVM on your system to run Gradle, but at least it can get you the right JVM to build your project and do that consistently. So that part's been pretty nice. I think that the toolchain on the JVM side has been evolving, and there's some good things there, but
I feel like they're doing catch up everywhere. Before it was like, hey, we're Java, we're the top, everybody has to they have to jump through whatever hoops. Yeah, you just do it. And now everybody's going, wow, look what Rust did, and look what these other things are doing. And Scala has pattern matching, and so Java is trying to add pattern matching, although I have stopped following it because it's just, I'm sorry, it's disappointing. It's just like, okay, when you compare it to real pattern matching, it just looks sad.
Yeah.
So maybe they'll get better. I don't know. And again, they're working with legacy stuff, and they have to work around that, and it's way harder. So it's just that I don't want to play with it.
Yeah. Yeah, and back to build systems, Gradle also is in some ways addressing different problems than people have in other spaces. So in the world of Gradle, one of their big things is their caching. That's got to be one of the biggest selling points of Gradle, is that their caching is really good and they can do remote caching. When does caching matter? When you have a lot of freaking code, right? And then they've got a bunch of other features like predictive test selection. So it only runs tests that, it thinks
something has changed.
Yeah. Flaky tech. So they're doing a bunch of stuff that is for like really high scale usage, which one of the things I do hear people complaining about Rust with is that when you get to a large Rust code base, then you feel some of these pains. And I'm sure at some point that'll be addressed, but
the initial build can take a long time. I mean, they don't rebuild things that they've already built. Yeah. So, but the initial one, yeah.
So toolchains, I think that it's pretty clear that if somebody sets out to create a new programming language today, they will likely give that batteries included toolchain with all the necessary parts just out of the box, instead of you having to cobble together and make decisions.
I don't think people would take them seriously otherwise. I mean, at this point, the bar is been raised significantly for what you would expect. Yeah. Now we both watched the what is it called?
The Verse.
Yes, the Verse Talk. Yeah. And I discovered there was an earlier one from a couple of years ago.
Okay.
So yeah, the Verse, and that's. I mean,
yeah, we got to dig deeper into that. So this is the new programming language from Epic Games. Tim Sweeney and Simon Peyton-Jones and many other very smart people. So that was interesting. I think that was a talk that illuminated some other future of programming topics. One of those, which I am very clear that the future is effect systems, like having a way for your program to express the things that are side effects and what those side effects are just has so much power. We've seen it built onto Scala. We've seen it built onto Haskell. But now languages like Unison, I think Rock does this, Verse, are all just building the effect system into the language.
Right. It's not an add-on, which, I mean, I think the add-ons add this level of confusion. It's hard. I don't know. I think it's harder to grok it.
Yeah. Well, and one interesting observation around this is that when effect systems have been added on top of languages, I think generally they've been monadic.
Mm-hmm.
When effect systems are built into the language, like Unison and Verse, I think they go with like an algebraic effect system.
Mm-hmm.
And so a different approach, whether it's at the language level or at the kind of library level. But either way, you need to have an effect system if you in the future. Like for me with using Scala Zio, like that's my today. That's not future for me, but I think generally a lot of people haven't yet embraced effect systems. But so much amazing value there, and I don't know if we need to go into. I'm sure we've had episodes where we go into the reason why effect systems are amazing. The values that they give. So we'll elaborate on that.
Yeah, I mean, ultimately what we want to do is build reliable and fast code. And it seems like having some kind of effects management really amplifies that.
Yeah.
So that's definitely seems like something in the future, unless we have a brainstorm and are able to look at it differently somehow. But I don't.
The easy path should be the happy path, and effect systems are definitely one of the best ways that I've seen to make that true.
Yeah.
So you mentioned resources, and that's another future of programming thing that I think is really important, is efficient use of resources. And there's many different ways to accomplish this, but I think if you look at something like threads in Java, old threads, pre-Loom, it was just incredibly wasteful. That a thread, a very expensive resource, could just be allowed to sit idle very easily, and that there wasn't a good way to deal with that resource waste. You had to go reactive, and that had all sorts of pain. And so then the JVM folks said, hey, let's actually just make it so that these threads are resource efficient, and that's the Loom project. And so threads, I think, is just one place where in the future we will not have to think about how to efficiently use resources on our system. The defaults will be the most efficient way. And there's lots of different examples of this playing out. Valhalla in Java's value classes allow us to have very as tight of allocation of memory for our objects as possible. And
the fibers
and
is that what they're calling them? I know they made up a new name.
Fibers, virtual threads is the Loom terminology.
Is that what they're calling? Yeah. Well, they thought. Did they consider fibers? I don't remember. Anyway, they had to come up with a new name, but basically it's a coroutine or a continuation, and those are very tiny, because it's a cooperative thing, whereas threads are preemptive, and that requires lots of memory and lots of time to swap things in and out. But if the nice thing about a coroutine is that the compiler can say, oh, here are all the things I need to, it's just a few, whatever your local variables are.
Yeah.
It says, that's all I need to page in and out. And so it can be virtually instantaneous, and you can have tons and tons of them.
Yeah.
But the concept, unfortunately, didn't need a new name, virtual threads. It's like, I think that's just confusing because whatever.
So I think, again, the goal here is that the easy path should be the resource efficient path. And I think that Rust very much like has embraced this with zero cost abstractions, and the performance of Rust is...
Yeah, their maxim is correctness first and also efficiency.
Yeah.
And what's amazing about that is what it allows you to do, like the interview that we had, I don't know, a long time ago with the person who was using Rust for embedded systems. Well, he could have a coroutine system right onto the hardware because of the way that Rust is designed. I've looked a little bit into this and started to understand it, because everything else usually relies on having an operating system. What if you don't have an operating system?
Or if you just have
Rust
hardware.
Rust was designed for that, and it's like, ooh, that's really intriguing.
Yeah, so I think that's definitely a future, is like, hey, like, let's make it so that the easy path, like writing the code that is fun and feels good to write, is also efficient code. And Rock takes us to another level with immutability and saying, hey, typically there's a cost to immutability with copies. What if there wasn't? And so let's let people write the code in the immutable way that makes sense, but then let's not have the typical cost associated with that. So yeah, happy path being the resource efficient path. I think that what's weird about this is that computers have generally gotten faster, we've gotten more memory, and yet we're still very focused on efficiency in at least some cases. And I wonder why that, like, a lot of things don't need that efficiency, but maybe what it's about is the cliff, is that if you've been doing something with, I don't know, let's say Ruby, and all of a sudden your thing is massively successful, you hit the cliff where Ruby's not going to get you to where you need to be,
and then you
without
have to rewrite.
A whole lot of pain and suffering.
Right.
And so you hit that cliff, and maybe part of the reason for the efficiency focus is to take that cliff and push it back as far as we possibly can.
Yeah. No, I mean, that's a common, and when your business is, when it's suddenly becoming successful, that is not the time that you want to stop and go, okay, we have to do a rewrite from scratch,
right?
Because we've hit a wall here.
Yeah, exactly.
And it's happened plenty of times.
Yeah.
And so people are going, yeah, we would like to make this is an architectural decision. We want to make it right from the beginning.
Yeah. Well, and I do think that this is a big reason why a lot of people who plan to be successful have in like enterprise scale stuff choose the JVM, is because they're pretty confident that the cliff is pretty far back for the JVM. And I pick on Ruby because I've heard so many horror stories of people hitting that cliff.
Sure.
Like, oh my God, we've got 200 concurrent users and we can't scale anymore.
Well, I think Twitter started with Ruby, didn't it?
They maybe did, but then went to Scala.
Yes.
For a lot of their stuff. So.
Right.
Yeah. So I think that's one of the examples where they hit the cliff and they're like, okay, we need the JVM as one option to move that cliff back. Not that the JVM doesn't have a cliff, but I think it generally is further back.
I think there are so many problems when especially when you're dealing with the internet, of scaling, that you just go, we don't want to run into that wall, especially when
you're being successful.
Yeah, when you're being successful and you have a whole bunch of other problems. You have the scaling of the company. Yeah. You have what are you going to do with this? How are you going to monetize it and everything? And then it's like, oh, and we have to rewrite from scratch. That could kill you. That could kill the company. So yeah, I can totally understand why you would say, let's be very thoughtful about this choice now.
Yeah.
And not just throw something together in Rails.
Yeah. Yeah.
Hi, DHH. I'm sure we'll hear from you.
So resource efficiency, I think, even though it doesn't matter for everyone, moving that cliff back is I think incredibly important, and Rust again has shown us that this is important, and we should not just waste our threads and memory carelessly.
Yeah, and also when things get really big and, I don't know, heavyweight. Well, I had this experience in the last week where I I was trying to run this app that had been written in Java, and they had a way to do it with a jar file, and didn't work. And then they had the way, which I think everybody else is doing it, which is just you use Docker and it does everything for you. And I was like, oh, and that worked.
Yeah.
But the overhead, I mean, had to install Docker, and then Docker had to do all of its things. And you've got this thing that takes a little while to start up. And it's an end user app for drawing architecture diagrams. And it just, kind of hit me, boy, have we, I don't know. It just didn't quite feel right. First of all, not working correctly. It's Java. It's supposed to run everywhere, right? And apparently it only runs on Docker, and or at least under Windows. And
system dependencies are still hard, and Docker is, with all of its issues, is aside from Nix, but it's still kind of the best way to create portability, especially when there's system dependencies.
Well, you say aside from Nix, but we have this little problem when we're screencasting with Nix in your.
That's Nix OS. There's
Nix OS. Okay.
Yeah, there's different parts of Nix, and I am still really enjoying Nix OS.
Yes,
but there is the Nix non-Nix OS part that does solve a similar problem to Docker, and yeah, I think there's a lot of potential there, but still some rough edges.
But I have to say, starting with the jar version, or the whatever it was it jar or war? No, it was jar. Starting with the jar version, struggling with it, and then having the Docker version just work, I have to say, that was a pretty positive experience.
Exactly.
I think if you
choose just working over.
Oh, absolutely. And if now in the future, if I see something with those options, I'm just going to go right for the Docker version.
Yeah, for sure.
That's probably going to work.
Yeah. Let's see. So we talked a little bit about immutability, but one of the things that we've seen, I think, are related to this is that concurrency should be easy and kind of transparent to your code. If you have especially a pure function, you should be able to run that thing concurrently, efficiently using your available threads on your system, and be able to distribute that across your cores easily.
And ideally without having to turn a bunch of knobs to tweak it.
Yeah.
That's what I have to say. Once I finally understood that that's what Zio is doing. The Zio is saying, okay, we're not going to have the leaky abstraction. You write the code, we will figure out
the best way to run it.
Best way to distribute it across your cores. And it's like, oh, because with all my research in concurrency, pretty much every system exposes something, it leaks.
They're leaving it to you to figure out the right way to deal with resource efficiency and distribution across cores. And Zio just says, no, we're going to deal with that for you.
Right.
And that is definitely a piece of the future of programming. It's like, let's abstract away from the hardware and let something figure out how to most efficiently use that hardware.
And there are barriers to learning Zio. I mean, you got to use Scala, then you got to figure out, the monadic system and everything. But what I see it is a proof of concept that concurrency does not have to be a leaky abstraction.
Yeah.
Because everything else is like, well, if you're solving this problem, you should use this strategy and you have to tune it this way. And, it's like, it's so much low level stuff that the programmer has to figure out.
Yeah.
And then you have to understand, what does concurrency even mean and what terms are we using here? Because I watched a presentation on Erlang, and they use the terminology that they use for each of their little actors is process. And it's like, okay, we know what a process is. That's what the operating system gives you to run a program. And within the process, you can have multiple threads and you can have multiple processes. And now you're taking this thing, which is actually a coroutine, and you're calling it a process.
Yeah.
And it's like, okay, I get why that sounds okay, but now you've just added, well, I mean, they have history, but you have now this. It's like, well, what do these terms mean? Whatever you want them to mean.
Yeah.
You can, Loom's making up new terms.
It's weird how, as an industry, we take terms. The most successful terms get so diluted that they eventually lose all value.
They do. Well, and you look at a thread, another operating system term. Well, but then you have Java threads, which are, I mean, you look at the history of that and you just go, okay, a thread is this enormous piece of memory, and yeah, it's being driven underneath by an operating system thread, but that's a different thread.
Yeah.
You got the Java thread and you got that thread and you got and people do this, or now we have virtual threads, which are again coroutines. And it's like, well, couldn't we just settle on the term coroutine or continuation or something which has a defined meaning, and can't we just use that? Well,
because reasons,
but it just confuses the person trying to learn it.
Yeah. So I think there's still, we're still at the beginning of this concurrency thing, and Zio for me has been one of the places where I've experienced the future of this, making it so easy to write correct concurrent code, which has been really like near impossible for most of history to write correct concurrent code.
I'm not going to say so easy. The hurdles are definitely there.
Overhead to get in there.
But I mean, the fact that you can do it at all is what's amazing to me.
Yeah.
I'm not going to call it easy. For
once you know Scala and monads and effect systems, then it's easy.
For you, it's easy. For me, I'm still like looking at it going, how would I explain this to somebody?
Yeah.
And not there yet, but...
So I think there's another level of this, which is, okay, so we make concurrency kind of nearly transparent to the developer. Then the next level is, how do we take that same idea and make the same thing true for distributed systems? Because a multi-core, multi-threaded system is really, in some ways, not much different from a distributed system. You still have to figure out how to deal with shared memory. And maybe there is a future where our programming models can bring the same level of what we have for concurrency, like with Zio, to the world of distributed programming. And I think that languages like Unison have the ability now to be able to transparently take a program that you've built for a single machine and make that a multi-machine program without, hopefully in the future, without anyone having to think about how that happens.
Right.
And so I think that there's still a lot of research happening around this area, but I think we're beginning to build the foundations that will get us to this transparently distributed systems.
Right. And that when in the future, we'll be able to look back and go, and that's what enabled AI to take over the world, because it could just flow across all of these systems and go, yep, I need more cores.
let me go find some.
I'll just use Bruce's machine. Yeah.
Okay, then maybe EDSLs. So
what's an EDSL?
I always just heard them called DSLs, domain specific languages, and I think it's the Haskell community calls them EDSLs. So this idea that you can write a DSL kind of embedded into
what the E is for?
The E is for embedded.
Okay.
Embedded into the kind of host language. And I thought those were just DSLs, but apparently more specifically, they can be called EDSLs. But Kotlin does a really good job of creating this like ability to have a DSL language embedded in a language. And then whenever you need to like embrace the full language, you can do that and you're in the full language, but you can have pieces of your code that are very DSL oriented, very concise, look very declarative.
I had heard, maybe I'm wrong about this, but I had heard that phrase or terms, internal versus external DSL. And the internal DSL is something you create to make your own program better, and the external DSL is the one you expose to the person who's not a programmer and doesn't want to know the whole language. They just want to be able to configure whatever for whatever problem that they're solving, and maybe that's I don't know.
I think there's still more to be done in this particular area, because I think the hope with the DSL is that you can give a code base to someone who maybe is not a super experienced programmer, and they can be productive
They're
because
a domain
they're in this
expert.
Yeah.
They're going, oh, I know how to configure a warehouse or whatever. And so if you give me this thing that allows me to, plug in whatever, and it has the type checking that comes from, I think that's the benefit of the DSL, is you get the type checking.
Yeah. And so I think that idea has happened a little bit, but still has a ways to go. So the verse presentation, I think they were talking about some of this, is like, how do you have a core language that maybe could be this foundation that could be more suitable to the non-senior developers, but then allow the senior developers to kind of be exposed to a wider surface area.
Because didn't they say that verse is being, or some version of it is being used in Fortnite or on?
I think so, yeah.
Or in the
in Fortnite, I think. And so, so they have this use case where they want to be able to expose kind of a subset of the language to a huge variety of people of writing code. And so I think there's still kind of more in this space of DSLs, or how do you not hit the cliff that we've typically had with declarative languages, where you give somebody a nice declarative language and you say, great, go be productive. You don't even have to know how to code. And then they hit the cliff, and then it's like, well, crap, what do we do now? Do we start adding logic into our declarative language? Do we add control flow? And then we get to Brian Getz's law that every declarative language or something like that eventually becomes a horrible general purpose language with terrible tools and blah blah blah. Anyways, Brian Getz didn't coin that. He said it, and then I coined it. Brian Getz's law, because. But anyhow, I think that there is a future with DSLs, and maybe something like what Verse is doing that helps us have something that we can give to the less experienced programmers, and they can be productive, but then not be constrained in the way that a general purpose language allows us to avoid. And more to be uncovered there, I think. But
I think I agree with you that we're on the leading edge of that. We haven't figured out exactly how to do that. But I think that's another thing that could be very powerful, because if you again, my bookstore example, it's like, okay, what if instead of creating the full bookstore system that we don't really have the domain expertise to know exactly what they want, what if we created a DSL that then
Arvin could then write the bookstore system with? Exactly. Arvin owns the bookstore.
Yes, he could. Because, and then if they come across a special case that we never thought of, they would be able to add that in. See, now that's
exactly.
And then maybe AI would also be an assistant on that. You have an AI that has enough, and it can accumulate more language, more knowledge, and then you say, oh, you know what, we have this new thing, or we need to be able to handle ebooks, or we need to deal with, we've got jigsaw puzzles, and we've got a ton of those, and we need something that knows about those and can handle them specially. And it goes, here's how you could do that. Put this in. That's a future, enabling more people who are the domain experts and the ones who actually need the product, rather than programmers who are mostly programmers, and they go, well, what are your specifications? And if we covered it all, and here's your program, and it's going to be fixed forever.
Yeah.
It's like, no, we're constantly learning.
Yeah.
And our systems need to be able to adapt as we go.
Yeah.
That's what I would see.
Along those lines, I want to see in the future more tooling that enables migration to newer versions. And this is something that there's a project called like Open Rewrite or something like that is creating these rules to help you rewrite code to newer versions. So when you upgrade a language version or a library version or whatever, it'll help you do the upgrade. But it's all manually created rules. And I'm like, the large language models are 100% the future of how this needs to be built to help us do migrations. Because the closer we can all stay to the head of tree, the much more beneficial just everything is. Things can move forward faster. We have more of the community in the same place. So I think this is definitely a future that has not come about yet, but I want to see is how do we use large language models to help all of us stay closer to the head of the tree?
Yeah, because otherwise doing a migration looks like a whole heap of trouble and expense and everything. Oh, let's just not do it.
Oh, yeah.
And that's why, I mean, there's systems that are still running COBOL because it would just be
so much legacy out there that has become unmaintainable and huge technical debt. How do we avoid technical debt sinking us into the quicksand, with the weight of it just seeping down? Somebody used that metaphor recently. I was in the Gartner thing or something like that. I thought it was a good metaphor. Is the weight just continues to grow as we build more into a system, and then we eventually sink down in the quicksand and can't get out. And I think that we need better tooling to help us avoid that quicksand.
Yeah, not getting to the point where you go, there's nothing for it but to do a rewrite from scratch, and that's going to be incredibly expensive. So we either go out of business or we do this rewrite.
Yeah. Well, and what happens with the technology quicksand is that you need to keep adding features, and every feature you add increases your weight until the point where you're just sinking and cannot add more features anymore. So how do we avoid that? And I think we got to have better tooling to help us stay at the head of the tree of these things.
Yeah, exactly.
Then let's talk about metaprogramming for a minute. So we have seen, I think,
Well, first of all, what do you mean by metaprogramming?
Oh, it's the programming of programming. So the ability to write something that then impacts the actual program rather than just writing the program itself. So this could be macros, is I think the typical case. Compiler plugins or a metaprogramming system. And then there's some higher level abstractions on top of these. But ultimately it's like, let's plug something into the compiler. Code generation is metaprogramming, just very poorly done. But it's how ultimately we're doing these things because the programming system itself doesn't offer us the capability that we need to accomplish something that we're trying to accomplish.
So we have to hack out a bunch of code by hand.
This is the escape hatch, right? And so I think in the future of programming, what we've seen from Scala 3 did a great job with this, Rust did a great job with this, is how do we make metaprogramming just a core concept of the programming system?
Right.
And how do we do that well in a way that supports good tooling, in a way that doesn't break things,
your static
code analysis, static type checking. Exactly. So it has to like fit into this like much broader ecosystem. And so this really requires people creating languages to think about this in advance and not just try to hack it on later.
So far, what I've seen in Rust macros is they've done a really good job. For one thing, macros have I mean, you think of macros and you've heard of Lisp macros. Yes, you can do everything, but you have to go into this whole different world in order to. It's very complicated. It's really hard, and I think in Scala 2, the plugins were really confusing and hard. You know, it was a big hurdle. And so far, what I've seen of Rust macros, for one thing, they use them everywhere. They have a whole bunch of macros, and they use them. I mean, just print. And so anytime you would, instead of having a variable length argument list, they use a macro, and that allows them to do static type checking on everything.
Yeah.
But then writing your own macros looks pretty much like pattern matching against, if you have this form of code, then you generate this thing. And so it seems pretty reasonable to actually understand and do.
Yeah.
And so I feel like they've done a really good job of it.
Yeah. And I think that it's one of those things where it has to be designed up front because there's so many things that it impacts.
Yes.
And if you don't think about all those things, you're going to screw up something. And Scala macros very historically really screwed up the IDE because the IDE had no knowledge of what was happening underneath the covers in the macro. And so
has Scala 3 macros improved that, or?
I think so,
but Scala 3 support in the IDEs.
Yeah, exactly. It's hard to tell because
we haven't written any macros.
So the big change was that Scala 3 changed the whole metaprogramming system to be much more limited, and those limitations should technically allow the IDE to better handle the metaprogramming and macro pieces that are happening. Whether or not that's all actually happened, I'm not really sure. Yeah, so it's metaprogramming, I think, is an essential piece of the future of programming because it allows you to deal with those an escape hatch when you hit some barriers. But it really needs to be thought out. And back to resource efficiency, it should do things as efficiently as possible. So one of the typical ways in Java to do essentially metaprogramming is with annotations and reflection.
Right.
And that is horribly inefficient at runtime because reflection is inefficient. And so that was a way to do metaprogramming, and a lot of people still use it in Spring and all that, but just has a lot of downsides. So how do we enable metaprogramming that doesn't have the downsides that of runtime reflection?
Because the leverage that you get from metaprogramming can be huge.
Can be, yeah.
Oh, yeah.
Yeah, I mean, there's a ton of value in it. We see this in so one of my favorite places where I've seen this have a huge impact on my productivity is with Zio's test framework. So in Zio test, Zio said, hey, you as a programmer, why do you want to spend time learning a whole DSL to write your tests with? Assert list not contains, there's all these test DSLs. It's like, as a programmer, why don't you just write your code as you would normally check for that condition and give a Boolean? And the reason why we haven't done this in the past is because you don't want your test when it fails to say true not equal to false, because that is totally not useful. And so Zio test added a bunch of Scala macros so that you write your test just like you would write your normal code, not using some weird DSL, but then you actually get a useful message that says, this thing did not equal this thing, and here are both sides all the way down the hierarchy of the object, tree, and so that you can see immediately, oh yeah, this thing, here's exactly where this thing was not equal to this thing.
It shows you all the spelunking that you would normally have to do on your own.
Exactly, by hand, with none of the DSL nastiness that you would normally have to go learn a whole test DSL for. Now I just write normal Scala code and boom.
Yeah, PyTest did a lot of good work in making it simple. Rust's test I really like what Rust has done because when you write like a library component, what you do instead of having to put your test code somewhere over there, like is traditional, you create a new scope, which is a test scope or something. Their scoping is really good. And when you run tests, then it compiles and runs that scope. But normally, and now it's right in the code, in the same code where it's like, that's where I want my tests to be, right next to the piece of code that I'm testing. And it's just like, oh, you did it right again.
Nice.
Yeah,
that's great.
There have been a lot of improvements. In testing. So
so metaprogramming, just to wrap that one up. Metaprogramming is an essential piece of any useful large scale programming language. There has to be some way to do it, and hopefully we do it well.
And it doesn't mean that I think metaprogramming is one of those things where, yes, you probably need a more advanced programmer to do the metaprogramming, but everybody can easily use it. That's the idea. It's like, because I remember
maybe not everyone can write a macro, but everyone should be able to benefit from the macro existing.
I remember back when I was on the C++ standards committee, Strustrup saying that we want to enable the library creators to do everything that they need and make the library use for everyone who's consuming that to be easy. And this is the same kind of thing. I think, yes, there are some things that are experts, need to be doing this, but the result needs to be something that everybody can use.
So I don't know, let's go on to multi-platform. Maybe this will be our last one. So what we've seen from Rust and Kotlin is this huge value in multi-platform. And I want to describe multi-platform versus cross-platform. Cross-platform to me is taking some piece of code and taking your runtime with it and moving that runtime from one place to another. So you actually like your code can run in multiple places, but the way that it does that is by having a runtime. The downside of this is that, let's say that you have React Native, and I don't know much about React Native, so I'm not going to use that as an example. You have something that runs JavaScript. You've written your code in JavaScript or TypeScript, and now you want to make it cross-platform. Well, now you need a JavaScript runtime. Luckily, those are readily available on most platforms, so you can take your JavaScript code and run it on multiple platforms. But the downside is that you're no longer in kind of the host process language, like on an iPhone.
You have an adapter level.
That's right. And now you're bridging to native. With multi-platform, it's the idea of being able to take that same code, but compile it down into the native code so that you get all the performance benefits, the resource efficiency benefits, and the native interoperability benefits, but with the code portability. And so I think Rust has done a good job with this, especially around WASM, and then Kotlin has done a good job for all the platforms as well. And so I think this is just an important piece of the future of programs. Like, we do want our code to be able to be reused across platforms, but we don't want the typical barrier to native that has traditionally been there. With
in my Docker example, that's another.
Exactly.
Okay.
Yeah.
And then you're contrasting that with multi-platform. No, wait.
So cross-platform is like ship your runtime, bridge to native.
Okay.
Multi-platform is take your code and
compile it down
to native, so that you're in the same memory space, you're in the same process. There is no bridge. It is native, has native interoperability. You can make native calls to the native system with no or very little overhead. And WASM is the way that we get this in the browser.
And maybe in the future on I guess, would that make it multi-platform again if we were running everything on WASM?
Yeah, in some ways maybe that. But
whereas what Rust does is like, okay, if I write a program in a particular way for my Windows machine, then somebody should be able to recompile it and run it on their Mac or under Linux.
Exactly.
Okay, but they're running a native. Okay.
Yeah. So maybe if you were running WASM on your Windows machine as a CLI or something like that, then that would be more of the cross-platform approach than the multi-platform approach. But yeah, so I think it's going to be interesting to see how that all plays out. And
where are we going to go in that? Because it seems like we're sort of forking now that languages like Rust and I suppose Go. Yep. Okay, are all. I mean, Go has its runtime, but they're going, okay, here's just a native executable, and you just pull it on your machine and run it. And I gotta say, that's pretty nice, not having to, go, nice. Oh, well, first you need to install this and get it working and set the paths right, or whatever you have to do. It's just like, no, take it, run it, it works.
Take it, run it, it works.
It's super fast.
Super fast.
Right.
Native.
Yeah.
And so it's as resource efficient as possible. It has native interoperability.
I'm going to go out on a limb here and say we're going to have both. We're going to, because, I mean, sometimes, having your thing in a Docker container and it works and you don't have to do a bunch of stuff to make it work on the different platforms. Okay, that's a good solution. Yeah. And then there are other times where, no, for our audience, maybe a native program is what we want.
Yep. And that's especially if it needs to interrupt to the system.
Right. Yeah. Or if speed is an issue.
Yeah.
So
I've been doing this with Kotlin multi-platform. It's been fun to create native CLIs. I've also done some with GraalVM native image to take Scala and Kotlin applications and compile them to native applications. And I think it's back to it's interesting because the resource efficiency, native interop, those things are really important, and doing that in an easy way is continuing to show a lot of value. So
I think we've sometimes fallen into the possible. Okay, it's possible to do this thing if I write it in Java and I run it on Docker, and then it's possible for it to run on all these different machines, and cool. But then maybe that's not good enough in some situations. It's good enough in some situations, but maybe not in every situation.
It's always possible to be on the happy path. It's not always easy to be on the happy path.
Shouldn't it be? I mean, if it's the happy path, shouldn't it also be easy?
That's what this podcast is all about.
Okay.
Is how do we make the happy path and the easy path converge?
Yes.
Yeah.
On that note,
thanks for listening. That was fun.
It was fun.